And now we jump here into ChatGPT March 23 version. As you can see, I have given ChatGPT here our classical structure. I say this is your instruction. You have a premise and a hypothesis, and answer now given the specific premise and hypothesis. And ChatGPT comes up here with a lot of different dependencies just given our two specific fields, a premise and a hypothesis. So, cause and effect. The premise describes a cause and the hypothesis describes the effect. The rain is falling heavily, the streets will flood. A spatial relationship. The premise describes a location and the hypothesis describes an object or an event. Or a temporal relationship. The premise describes a time period and the hypothesis describes an event or change that occurs within that time period. For example, the sun is setting, and the hypothesis the sky will turn orange and pink. Comparison. The premise describes two or more things, and a hypothesis makes a comparison or a contrast between them. The cake is chocolate. Hypothesis, the vanilla ice cream will taste different with it than the strawberry ice cream. Or a generalization. The premise describes a specific instance, and the hypothesis makes a general statement or conclusion based on that example. For example, the cat always scratches the furniture, and the hypothesis is cats are destructive pets. Yeah, absolutely. Inference. The premise contains certain information, and the hypothesis is a conclusion drawn from that. The store is closed, it's too late to buy groceries. Probability. The premise describes a situation or event, and the hypothesis describes the likelihood of a particular outcome. The weather forecast predicts rain. Hypothesis, the baseball game may be postponed. Association. The premise describes a relationship between two or more things, and the hypothesis describes how that relationship affects a particular outcome. Example, the traffic is heavy on the highway. The driver will be late for the meeting. Causation. The athlete trained hard every day. The athlete will perform well in the competition. Contrast. Two or more things are different. The hypothesis describes the difference between them. The dogs bark loudly. The cat meows softly. Can be used to create a variety of templates for fine-tuning things. So, if you want to see this, 10 template forms for you. Now, isn't this beautiful? It's doing all the work for us. We have inference, probability, association, causation, contrast, generalization, temporal relationship, spatial relationship. Number 9 is comparison, and number 10 is cause and effect. So, and here we go. For template number 1, I get now 10 examples. I can make 1000 examples for template 1. And from template 2, I can make another 1000. And from template 3, I can another 1000. So you see, this is how you self-instruct a data set that we can use further on to self-instruction fine-tune an LLM. And this is why we use here ChatGPT, or if you have the money, you go to OpenAI, you pay for the API access, you write a Python program, and instead of me typing here these commands in a Python program, I say, hey, create template 1, create from template 1, 1000 data set, from template 2, another 5000 data set. And this is how you do self-instruct data set. But you know what? Let's switch to a complete different data set. This is the AG News data set, and we have here URL. We have a very short headline, we have a short paragraph, and then we have the full text. And as you can see here, this is a data set. And now we can ask, hey, is there a way that you can create a more complex template structure for us? So we construct the template 3. We have instruction, read the following and fill in the missing information for a headline, paragraph, and URL. Then write a summary that best describes the article. So, okay, missing information, topic, supporting information, summary. And here we go. 1 is the headline. 2 is the paragraph. 3 is the URL. Of course, this URL does not exist, just to tell you, né? This is just does not exist. Everything is created by chat. Missing information, Jason alone supporting, yes, summary, plans, and launch saber. So what you see here, beautiful. This template 3, this we gave a feedback. This is gorgeous. Here we have now a template where we can have a very complex data structure, even with some meta information, with some additional information to the main core of the task. So this here illustrates perfectly the difference between an instruction fine-tuning, here an self-instruction fine-tuning by ChatGPT or your GPT-4 fine-tuning compared to the classical fine-tuning, where you do not have this amount of information. Look at this amount of information, and this is just one instruction data set. So here we can now discuss what is the difference between self-instruction fine-tuning and the pure old classical fine-tuning. So in general, what other forms of instruction fine-tuning for LLMs can you generate? My goodness, unbelievable! So let's have a look here. So in general, what other forms of instruction fine-tuning for LLMs can you generate? So here we have, for example, now template number 4. The instruction is read the given prompt and write a response that best answers the question or completes the statement. So I have a prompt and a response. This is the structure of my instruction data set for fine-tuning. Example for the prompt now. What are the benefits of exercise? And the response is exercise has numerous benefits: improved cardiovascular health, increased strength, endurance, yes, yes, yes. Or template number 5. Read the given text and answer the following questions based on the information provided. So we have a text, and then we have question, the main idea, the key details, and what conclusions can be drawn from the text. This is an instruction data set you can create either with a data set, a classical data set that has this information, or you ask ChatGPT or GPT-4 to come up with this, like we have here. This is now the example by ChatGPT March 23. So for the text field here, we have in recent years, the use of renewable energy sources has become increasingly popular as concerns about climate change and environmental sustainability has grown. Questions: what are the main idea of the text? Key details. Yeah. So A, the main idea. The main idea of the text is the increasing popularity of renewable energy sources. The key details are B, solar, wind, and hydropower are mentioned as the most commonly used sources of renewable energy. And C, well, conclusions can be drawn from the text. It can be concluded that concerns about climate change and environmental sustainability are driving the increased use of renewable energy sources. Absolutely beautiful structured text that you can use now as an instruction template for learning your small little 6 billion, 7 billion parameter LLM, 13 billion ALPACA, whatever you like. And template number 6. Okay, let's do it. Read the given passage and identify any errors or inconsistencies in the information provided. So we say here, the passage of text is yes, yes, yes. And the errors are no errors. Okay, or another template. Read the scenario and write a response that best addresses the situation presented. The scenario: you receive an email from a client who is unhappy with the service they received. They have outlined several specific issues and are demanding a full refund. How would you respond? And now you have in your structured answer, in your structured data set, the response here, number 2, and the response here, the data set that GPT created for you, that you can now use this data set to instruct, fine-tune your own LLM is the response. I would begin by acknowledging the client's concern, offer to address each issue and raise and work to find a solution that meets their needs. So you see, this is beautifully. So we are now at the part where we say, okay, to make it absolutely clear, what is the classical fine-tuning? This will be here in the blue sector here on the right-hand side of your screen. And what is this self-instruct or instruction fine-tuning if you do not do the self? If you use a classical database and just change it to an instruction-based fine-tuning dataset. So here we go. Fine-tuning is clear. You fine-tune your LLM, your transformer, on a single downstream task. This is classical. We do this for years. Sentiment, for example. I have the data. This movie was nice. Sentiment is positive. This is the data set I provide to my LLM. This is the training data set, and now the training data set understands, or the LLM understands, that nice has some positive connectivity. This is what I call a zero form of data, because there's nothing more to it. Nice, positive, zero. Self-instruct or instruction fine-tuning is what I call a two form of data for self or only instruction fine-tuning. And you might ask why. Now let's have a look here at the data set. In fine-tuning, this is our data set, 2 lines. In instruction fine-tuning, this is our data set. You see, there's a lot more information to it. Now, remember at the very beginning of this video, I showed you here on ALPACA in real time, we had input data, we had instruction given, and output data were created by ALPACA LoRa. So again, in the input data, we had now complex structures. The bees were humming in the sunshine in my garden, while an Airbus crossed the Atlantic. There are 2 different actions happening, but I put it in one data set. With the instruction, I address both parts of the sentence if you want. On the one hand, as I change the animals to elephants, so this is the first half of the sentence, and the airplane to another jet. So you see, here I can address multiple tasks if you want, that in the pure fine-tuning would be an additional downstream task. And this is here the beauty of a more complex data structure for fine-tuning. And I will show you when we will use this. The output data, as I showed you at the very beginning in my movie, the elephants were humming in the sunshine in my garden while a jet crossed the Atlantic. So you see, fine-tuning has a zero form. Self-instruct or instruction fine-tuning in general has a 2 form. 0, 0, 1, 2. Okay, this is important because we increase the complexity and the information density of the dataset we provide to the LLM to learn. So, FLAN by Google, FLAN T5, you know those systems, I have videos on this. What is exactly happening behind the scene? Now, FLAN now, with all the data sets that FLAN uses and are transformed now to instruction fine-tuning, the model is fine-tuned on a complex set of instruction, and it can generalize it to unseen instruction. And this is the beauty, because if you look here, it can learn quite a lot of data. And of course, the size of the model will be important, but more about this a little bit later on. So as more types of tasks are added to the instruction fine-tuning data, the model performance improves. And I showed you here the more types of tasks. If you have a template for causal interference, or you have a template for temporal interference, or a template for locational interference, the more different tasks, the more diverse tasks you have, the more the system can extract from this knowledge base and learn the LLM. So, clearly? Yeah? Okay, next up. Fine-tuning. Let's start with the classical fine-tuning. When fine-tuning a pre-trained language model without a structure in our training data, the model is typically trained to predict the next word in a sequence if you have an LLM, so the left part given the previous words. The objective function to use this is the cross-entropy loss, and you know this. Now, here in self-instruction or instructed fine-tuning, we use a structure. We have an additional structure on the data for instruct fine-tuning. The model is explicitly instructed to generate text also in a specific format. Remember, input, output, and the relation between this in the instruction. With more control over the output of the model that we have now, giving here an explicit format, as the structure can be used to enforce constraints on generated text, such as the order of the input fields, the formatting of the label, and the length of the generated text. If all the examples you provide have exactly 2,000 characters in the output, what do you think the system will generate after the fine-tuning? 2,000 words in the output. So, by providing the model with guidance on how the input data is structured, we can help the model better understand the relationship between the different parts of the input and improve its ability to make accurate prediction. The more complex you provide, the more the system is able to discover patterns in your instructed fine-tuning dataset. Okay, however, if for the downstream task at hand that we want to train our LLM, we have a clear goal. We want to train an LLM on one task. I don't know, sentiment or summarization or whatever you have, translation. The available training data is plenty, and I always told you, fine-tuning, we need tens of thousands, hundreds, thousands of data. And the training data is representative of the target task. It really fits the task. Then the classical regular fine-tuning may be sufficient and more straightforward. Because it is not so trivial to really construct here an instruct fine-tuning data set that really is clever so that the system can really learn a multitude of information. So, instruct fine-tuning is especially useful in scenarios where there's limited training data. You see, plenty training data, limited training data, or where the available training data may not be representative of the target domain, physics, mathematics, language translation. It allows us to transfer knowledge, and now comes the next fascinating part, learn from related tasks and domains to the target task, improving the model performance. This only works if you have a huge model, a huge internal capacity. If you go with an 8 billion parameter model, this is not enough. So, if the available training data is structured, it includes additional information, metadata, annotation, explanation. Instruct fine-tuning can be a powerful approach to improve the model performance. If you have multiple tasks or domains need to be addressed, instruct fine-tuning can save time and resources by training a single model. So all our layers just have one update rather than multiple models where you have one model for every fine-tuning run. This multiple task is now where you have to be clever. So, an example. An example is always good. Now we are only on instruction fine-tuning. So, I'll give you an example. You can read it, but if you want to fine-tune your LLM, at the same time at 2 tasks, so let's say we have sentiment analysis and topic classification. We can now construct or structure or template, or whatever you want to call it, the training data set to include the information about both the sentiment and the topic in the input sequence. So let's see. We want to fine-tune a language model to perform sentiment analysis and topic classification on customer reviews. So we structured the training data set in a new way, in a new form. And since we have an idea how the result should be, we now think, okay, how do I have to configure my training data set that I will achieve my goal. So easy. If you have a review by customers, so you have the text here. This is a great product, it works really well, and it is very easy to use. Beautiful. Now, if you want to have two tasks in one, you need a first, for the sentiment analysis, you need now the label, the class label for the sentiment. And for the topic classification, you need the class label for the topic. So here in the training data set that you produce so that the system can learn on this, you say, this is a positive sentiment, this is a great product, works well, easy to use. And the object, if you want, the topic that we are talking about is a specific product, a cream or whatever it is, I don't know. Or you have a text, this was terrible, so this is the negative example. Customer were awful, never do business with them again. So we have the sentiment is negative, and the topic is either the company or the experience with the company. So you see how you structure your data set, how you create here different templates will have an effect of the accuracy and the performance of your LLM. So you have to be clever constructing here templates that are really 100% focused on the job to do. Yeah. Each training example includes a text of the customer review along with the labels for both the sentiment and the topic, like product, company, restaurant, etc. So here you have it. Now, if you want to be an expert, read this, otherwise just jump to the next page. There is something very specific if you like to play around with this, and I do it here in my LLMs. Instruction fine-tuning can also help with handling more complex tasks by breaking it down into more simpler subtasks and providing instruction for each subtasks. The language model can learn to perform a complex task more efficiently. So let's have a look at this. Let's say, suppose we want to use a pre-trained language model to summarize news articles. Summarization is a complex task that requires the model to understand the main ideas, the important details of the article. If the article is 1,000 sentences, what is the main idea? What is the most important detail? 1-2 sentences, extract it, and generate a concise summary that captures the main idea, the important details of these elements. So, a very abstract example. So using now instruction fine-tuning instead of just fine-tuning, we can break down the summarization task into 3 simpler subtasks, such as identify the main topic of the article, identify the most important facts and details you want to stress, you want to find out, you want to underline, and then generate a summary sentence that includes the 2 before mentioned facts. So you see, again, how you construct your template for your specific task, for your specific data set, for whatever information you have to feed into your LLM to be then a fine-tuned LLM. You can really, here's where the human creativity comes to play. So by providing explicit instruction for each subtask, we can train the model to perform each subtask efficiently and then combine the subtasks to generate a high-quality summary. This is some of the beauty for me personally when I use here in particle physics, plasma physics, whatever you have, you can think about this breakdown in simpler tasks. Yes, there was a question about the size of the model. When is instruction fine-tuning really playing out? Where is it most powerful? And there we have data from Google. And Google, of course, used this from 0.4 billion LLMs up to a 137 billion free parameter trainable model. And here you can see in black, the black dotted line here is an untuned model. And you see this is it. If we have now fine-tuning our 0 form of data, I would expect the line here starting a little bit by 50 and then maybe going up here to 60, 70. So fine-tuning would be this line here. Hey. And then we look now at instruction fine-tuning. And what Google found on empirical, just testing it out, that If you go with a smaller model size, you see here 8 billion trainable parameters and smaller, you are even worse with instruction fine-tuning than the untuned model. But of course, if you provide complex data sets to learn, and let's say your brain, your model is so tiny that it does not have the capacity, that does not have the power to extract here the complexity and learn on the complex data set. If it just learns on a linear, data relation, you go below the untuned model. So if you go with 4 billion parameter model or 8 billion, you see you're still under the untuned model. You just cross over, it's a log scale, so let's say here with 10, 12 billion parameter models, you are on par with the untuned model. And the fine-tuning, you still have here the line on top of here. See, but then you see, the more powerful your model is, the more trainable parameters you have, the more, 8 GPUs you have, then, instruction fine-tuning becomes here the powerful instrument. Here it plays out its capacity because our transformer is big enough, complex enough to really understand here this two-form data information and extract here the information, find the patterns in the data set you provide for training. So this, I found here a beautiful empirical analysis by Google to see, do not use it on minimal models that do not have the internal capacity. So let's sum it up. Which is always good summarization. So we have two models, two ways. We can have a classical data set on Hugging Face, SNLI, where we have 175,000, 300,000 singular training data examples. We can use now, as I showed you here, we can convert this classical data set to an instruction fine-tuned data set that we will use this data set to fine-tune our LLM on specific tasks. Or here comes now OpenAI, ChatGPT, GPT-4 into play. If we as humans create, like in ALPACA, 175 single human written down examples, or if you just have 30 examples of some very specific biogenetic or pharmacologic, whatever you have, then you use this and you feed these examples into GPT-4. You go to OpenAI, you go to the API from OpenAI, and you say, hey, this is my minimal set of patterns. There is a complex pattern here in these 30 examples. So please generate for me a syntactic similar data set here, the missing 299.97K data sets that follow here this inherent pattern that you might discover in my 30 examples or 175 examples. The bigger your human written example size, whatever you have the data, the bigger it is, the easier it is for the system to discover inherent pattern in your data that you provide. And here, then, GPT-4 will create the missing 299.97K self-instruct fine-tuned data sets for you, so that you then also have 300,000 K training data examples for your fine-tuning process. So you always have to check, hey, do I have classical data sets that I can simply convert to instruct fine-tuning, or do I have to pay OpenAI? This is free, this you have to pay. Your credit card, here's your credit card somewhere. So this is where Stanford University paid, I think, $500 or something in the bracket of this to create your syntactic data. But of course, how good GPT-4 is in itself will determine how good your additional syntactic data are. So always go with the best GPT or LLM you can find. And if you want to see how we bring this complex data structure now into the data input pipeline to instruct, fine-tune our LLM, I'm sure my subscriber would be amazed how simple now the next step will be. I say thank you for watching, and I see you in my next one.